So, in atmosphere, a plane flies by moving its control surfaces to adjust the airflow over the wings. That's a solution that works in an atmosphere, but how exactly do you rotate and maneuver a spacecraft in orbit? Today we're going to talk about one of the most common ways of orienting a spacecraft in orbit. Let's discuss a reaction control system. I'm Colin, and this is Sci-Fi Deep Dive. Remember, if you enjoyed this video, to head down below and hit that subscribe button. So, once again, I'm going to throw out there that we'll be talking about real spaceflight a lot today, but these concepts actually are relevant within science fiction, and if you look at harder sci-fi elements like The Expanse, for example, you can see RCS thrusters a lot on screen. So, while I will be specifically referring to real-world spaceflight, these concepts do transfer over well to science fiction, especially harder sci-fi franchises. So keep that in mind as we move forward in this video. So let's talk about what a reaction control system is. So you have your spacecraft and it's in orbit, and you need to find a way to sort of rotate or orient that spacecraft to carry out, say, a specific engine burn or dock with a space station. Well, the easiest way of doing that is through a reaction control system. Now, there's actually other ways of rotating a spacecraft, like a reaction wheel, but most other methods end up meaning that you need to bring with you a lot of dead weight, and one of the things that's very important with spaceflight is weight. Every bit of weight on your spacecraft is a detriment. So you want to make everything as light as possible. So a solution that involves moving a large weight around, like a reaction wheel, would be a downside for most spacecraft. That being said, for some smaller spacecraft, it does make sense. But for something big like, say, a space shuttle or a Soyuz, it makes more sense to use something called a reaction control system. So to demonstrate a reaction control system, I have a little model of the shuttle here so we can sort of visualize how this works. So let's say you wanted to turn the nose of the shuttle down. Now, if you were in atmosphere, you could simply bend the control surfaces on the back of the wing and use airflow to angle the shuttle's nose down. But in vacuum, that's going to do nothing. There's no air moving over the shuttle's wings or the shuttle's control surfaces to affect that. And on a spacecraft like Soyuz, for example, that's even more useless because there are no real control surfaces on Soyuz other than the bottom of the spacecraft, which only adjusts re-entry trajectory and can't actually control it like the wing of an aircraft. So how do you do that in a vacuum? Well, the answer is reaction control thrusters. The shuttle has basically 3 banks of RCS thrusters, and I will be calling them RCS thrusters because that's the acronym commonly used for them. One bank is up here by the nose of the shuttle, and the other 2 banks are on either side of the vertical stabilizer. These banks consist of clusters of relatively small jets that fire in different directions. If you've ever seen a picture of the nose of the space shuttle and noticed all those little holes like right up here near the front, those are RCS thrusters, and they point in various different directions. Some point down kind of at an angle, some point out to the sides and up and forward. In the back, they point up, down to the sides and back, and that allows you to really maneuver the spacecraft by simply pulsing thrust out of each of those little tiny engines. And tiny, relatively. We'll talk about how they're not that small in a sec. But if you want to say turn the nose of the shuttle down, you could fire this jet in the front up and a jet in the back down, and that would rotate the shuttle. That same principle can be used to rotate it in basically any way. If you wanted to rotate it over its long axis, you fire one down on this side and one up on that side, and you can rotate the whole shuttle. Usually they're probably firing one in the front and one in the back in each direction. You can also use this system to actually translate the shuttle from one position to another. Now, when in orbit, a spacecraft is better off using something called an orbital maneuvering engine, or an OMS engine for orbital maneuvering system. On the shuttle, it's these 2 engines up at the top here, but there's a variety of different orbital maneuvering system engines from spacecraft across history. These engines provide a lot of thrust, but are a much larger ordeal to open and utilize. So these would be used for things like orbital plane changes and major maneuvers in a rendezvous operation, for example. But if you're, say, closing to dock with something like the International Space Station, or you're an Apollo lunar module coming up to rendezvous and dock with the Apollo Command Service module, you need a finer tool to be able to maneuver the spacecraft around, and that's where the RCS thrusters come in. Again, because if you were to take that same orientation and fire thrusters down in the back and down in the front, you move the whole shuttle up a little bit, and vice versa. You can use these thrusters to move forward, backwards, left, right, and up and down. This allows you to finally maneuver the shuttle around a docking target, be it a space station or a satellite you're rendezvousing with. And by the way, I keep saying shuttle because the shuttle is sort of the focus here, but this principle works for every spacecraft. We see this in, for science fiction relevance, The Expanse. A lot of spacecraft within The Expanse, we can see them firing and utilizing RCS thrusters, which is just another bit of testament to how realistic The Expanse is from a scientific perspective. So I've been referring to these thrusters as relatively small, but now I want to give you a demonstration for how they're actually not really that small. I have seen the shuttle several times, and the shuttle's, once again, a great example of this. There's a series, they're too small to really see on this model, but they're around the back thruster here. So I've been referring to those thrusters on the shuttle as small, but they are anything but small. And now I'm going to show you why I am well aware of that. The shuttle's RCS thrusters had a thermal barrier around them, the ones near the tail of the shuttle, which protected the engines. And this right here, and I'm a normal-sized guy, this right here is a thermal barrier from one of those thrusters. This is from the Space Shuttle Atlantis. This is one of the RCS thrusters' diameter. This is how big it is compared to a normal human. So it is actually quite a big engine that would be used to rotate the shuttle, which, mind you, is a fairly large spacecraft as far as spacefaring vessels go. But that just goes to show how big and capable these relatively small thrusters had to be to actually rotate a spacecraft of that size. And for anyone who's curious, that piece of thermal barrier is actually from Space Shuttle Atlantis. It was removed in the late 90s because there's actually a little tear in that one, but it's from one of the aft RCS thrusters on the starboard side, particularly the center upward-facing one. Just a bit of fun fact there. Anyway, the RCS system played a crucial role in rotating the shuttle. It plays a crucial role in Soyuz. It'll play a crucial role in Orion and Crew Dragon and the Starliner whenever they get that fixed and flying. It's an important part of any realistic spacecraft, and we see it in science fiction as well. And it's very important for docking. If you'd like to learn about the first docking of two-man spacecraft, the docking between Soyuz 4 and Soyuz 5, I'll leave a link up here to my video on the flight of Soyuz 4, talking about the important elements of that mission and why it's actually fairly historically significant, even though it's not talked about very often. And I'd like you to let me know down in the comments if you have anything else you'd like to learn about modern spacecraft, if you have any other systems on them that you're more curious about that you'd like me to dive into and do a bit of an explanation video like this one on to help explain how these incredibly complex but impressive pieces of engineering work. Just let me know down below. And also let me know down below if you have anything else like to see me cover in spaceflight, science fiction, or spaceflight history. And remember, if you enjoyed this video, to head down below, hit the like button, the subscribe button, and the bell icon so you get notified when I upload new videos. So for Sci-Fi Deep Dive, I'm Colin, and I will see you next time.